Greetings to both of my panels, Encik Muhammad Hafiz bin Jali and Dr. Ruzaini bin Hashim, and I am from Faculty of Electrical Engineering to present my final year project 1. My name is Sanjeev Rao. I am a student from BEKG and my supervisor's name is Dr. Sazwan Nazra binti Muhammad Azam. My research title for final year project 1 is Model Predictive Control of a coupled tank using Kalman filter. Introduction. In recent years, the performance requirements for chemical, petrochemical and process plants have increased. Development of new production plants to decrease wastage of material, minimize energy consumption and minimize effects on the environment to cope with the increasing competition and to satisfy increasing demand for flexibility requires the use of control engineering techniques to provide the desired and efficient control actions with simple and easy control algorithms. Coupled tank system is widely used in the industrial application to control liquid level in tanks and flow between tanks because of the problems in the process technologies. Coupled tank also provide liquid level measurements for feedback control purpose. Below is stated an example diagram of coupled tank system. Model predictive control has emerged as a powerful tool for dynamic optimization and control. It regulates controls that use a dynamic model to the response of process variables to changes in manipulated variables. It solves optimization problem at each time step to find the control actions that drives the predicted plant output to the desired reference as close as possible. MPC is an optimal controller which is based on minimizing error from the trajectory. It predicts the future behavior of the control output over future time horizon. It has a target value to be achieved in the future. Kalman filters is an algorithm that provides estimates of some unknown variables given in the measurements observed over time, containing unknown variables that tend to be more accurate than those based on a single measurement alone. By estimating a joint probability distribution over the variables for each time frame. Kalman filters has various applications. It have relatively simple form and requires small computational power. From the figure below, I would like to explain that Kalman filter combines the measurement and the prediction to find the optimal estimate. Problem statement. The first problem is that the unknown prediction of the future behavior of the control output over future time horizon. The second problem is the optimization problems at each time to desired reference as close as possible. The third problem is how good is the performance of model predictive control feedback law with the guide of multiple input and output configuration comparing with PID controller. Objective. The first objective is to determine the mathematical model of the system. The second objective will be to design a physical system by simulation or experiment results. The last objective of this project is to determine the comparison between dynamic and static Kalman filter. The scope of this project is to research and analyze on modeling the MPC of coupled tank system. Second, examine and monitor the performance of model predictive control of a coupled tank using MATLAB Simulink for dynamic optimization control referring previous studies on PID controller. Then compare the dynamic and static Kalman filter for estimation and prediction part. Then Analyze the design with comparing with PID controller. Lastly, check capacities and efficiencies of coupled tank in industry applications. This is the plan and flow chart of the methodology. First, we study on the previous research and elements involved in the project, which is the PID control used in previous studies. Then, we identify the previous problems or demands, which is based on the problem statement. Then, we define or generate initial parameters for the model, such as inputs, outputs, and equations. Next, we organize the flow and design of the project using a plant, which is our coupled tank. Next, we design a model to compute with kalman and MPC of coupled tank. Next, we determine the techniques to control the algorithms. Next, we analyze and identify desired liquid level of model estimation. If the predictions of the performance requirement is yes, we end. If no, we go back to determining the techniques to control the algorithms. This is the principles of model predictive control, which are a multivariable control algorithm that uses an internal dynamic model of the process, a cost function which is J over the receding horizon, and an optimization algorithm minimizing the cost function J using the control input U. Below figure is a model predictive control structure. It specifies sampling time and specifies the values of manipulated variable that we want to be linearized. In this function, the manipulated variable will be matched to the desired, so steady state is achieved. From this structure, we can know the set points is the reference to the model predictive control. The measured disturbance, manipulated variables, and unmeasured disturbance is the input for the plant. The outputs is from the unmeasured and measured value of the plant. This is the method of modeling the model predictive control. At the starting time, the process takes measurements, and for the objective and constraints, the process models have control actions and disturbance for the future process outputs. It solves above optimization problem to get best current and future control actions. Implementation of this best current and control actions is the way after the increase in time horizon. Kalman filters have relatively simple form and require small computational power, which is the Kalman gain, measurement residual, updated error covariance, and the updated state estimate. This is a model predictive control with Kalman filter of a coupled tank process. In the figure, we can see the Kalman filter is used as an estimator for the process, which is our plant of coupled tank. The MPC is the controller for the entire process. The control designer, controller, and the estimator is assumed in the model used in simulations. The process is the real model used in the simulations. This is a model predictive control system with 2 input and 2 output. This example shows how to simulate a model predictive control using MATLAB between the predictive plant model and the actual plant. First, from line 1 to 3, we define the plant model. We define the parameters for the nominal plant, which is the MPC controller of 2 manipulated variables, 2 unmeasured input disturbance, 2 measured outputs. From line 4 to 7, we design the MPC controller by defining the inputs 1 and 2 as manipulated variables, 3 and 4 as unmeasured disturbance. From line 8 to 9, The MPC controller will use the following unmeasured disturbance model. From line 10 to 12, we define the real plant model used in the simulations. We define the parameters of the actual plant in the closed loop with the MPC controller. From line 13 to 15, we simulate the closed loop response using the sim command. We define the reference trajectories and unmeasured disturbance entering the actual plant. From line 16 to 18, we create an MPC simulation object. Lastly, we run the closed loop MPC simulation with model of unmeasured disturbance inputs. The plant inputs and plant outputs waveform are shown in the figure below. From the simulation, we can see that the plant outputs has a different trajectories. For future works and conclusion, it is necessary to continue investigating to improve the Kalman filter's function. The most proposed Kalman filter is approached for the liquid control. Required measurements from tanks to perform the predictions in coupled tanks. Comparing with PID, the model predictive controller has multiple input and multiple output, which is more advanced, rather than PID, which do not have the predictive ability. This project's finding will contribute to the project's significance for future use of model predictive control in industrial application. Thank you for listening.